So today we're going to start our week on revision for topic of electromagnetism. So this week we're going to discuss on electromagnetism. Basically, we just do revision from the start to the end. So the first subtopic that we're going to cover for today is the magnetic field on current carrying conductor. Basically, this is the most simplest concept that we learn when we start the electromagnetism topic. So let's see number one here. Draw the direction of compass when current flow in the straight wire. So basically what we already discovered before, we realized that if there is a current flow, which means that there is electron flow, there exists automatically magnetic field around the wire. But now we want to investigate the direction of the magnetic field. We use the method of compass to know which direction the magnetic field is going to. Basically, the field pattern is can be identified using iron fillings. We put the iron fillings around the wire and it will form concentric circles. So that is the field pattern, magnetic field pattern. But the direction cannot be determined by using iron fillings. So we have to use compass to know the direction. Either it is rotated clockwise or counterclockwise. So in this case, how you're going to do that? We use the right hand grid rule. So the right hand grid rule, the thumb over here, the thumb shows the current, which means that it's moving towards the negative. So below is positive, above is negative. So and the rotation of the rest of the fingers determine the magnetic field direction. Okay, either is clockwise or counterclockwise. So in this case over here, the current is flow from down to up above. So this is the positive, this is the negative. So our thumb should be pointing upwards. So if we do our thumb pointing upwards, so our fingers here are rotating counterclockwise. So counterclockwise, which means that it's gonna flow look like this. And then our compass arrow is just follow the direction of counterclockwise. Okay, so as simple as that. So let's do number two. Draw the direction of magnetic field produced on the board. Again, this is draw direction. Okay, so we draw circles counterclockwise, and then another circles counterclockwise, and we can add one more counterclockwise. Make sure that the distances between these concentric circles, the smaller one is has a very near radius towards the wire, but the second one a little bit larger. Then the third one is more larger than the second one. Basically, what it means that the field is stronger near the wire and weaker farther from the wire. Okay, number three, draw the magnetic field pattern for carbon A and carbon B from top view. So again, using the right hand grip to notice the clockwise magnetic direction, but in this case it's reverse. inverse direction, the actually in the downward direction. So we know that still has a concentric circle, but direction is changing. So basically, if the current point is upwards, which means the negative sign is upward, and our direction is counterclockwise. But if the current is pointing downwards, and the direction of magnetic field now changing to clockwise. So basically, this is clockwise direction. So as simple as that, we just use right hand. There is current flow in conductor. So that's our first concept here. We use right hand rule when there is current flow in conductor, which means there exists battery or power source anywhere in the circuit or in the diagram. Then we can use right hand rule. So let's do number 4. Which compass shows the correct direction of the so we label positive here, negative here. Basically, the current flow from above to below. So it's downward. So we know that before this, if the current is pointing downward, then it is clockwise direction. By using right hand grip rule, each direction that we need to do, we just draw it look like this. Then just place back with arrows the same direction as the rule. So A definitely arrow is pointing like this towards the right, and the A also towards the right. B is so false, it's wrong. C is towards the left, so it's not correct. And D is upwards, so correct. So the answer is A. Okay, as you said. Number 5, draw the magnetic field pattern top view of each diagram below. So there are 3 types of current carrying conductor. We need to draw all 3, able to draw all 3. We know about single wire. So it doesn't specify us the direction, but we can just make the direction. Put the direction. So concentric circles. Again, we don't know the direction of the current, but if we assume this is positive, it is negative, then it is counterclockwise. Counterclockwise. Okay, if the direction of current is reversed, such as is positive and negative, sorry, it's not counterclockwise, this is clockwise. So then clockwise, so we just redo it again. Is it clockwise or counterclockwise? Counterclockwise. Okay, that's correct. What we thought earlier is correct actually. I'm confused with the direction of the current. So again, this is correct, counterclockwise. If the current flows from positive to negative, means the current moving upwards. Then our thumb shows upwards, and then our rest finger curl clockwise. If the current reaches this direction, which is this direction, then it will flow clockwise. Okay, so as simple as that. So basically, our circle looks like this. If we look above, then the current is flowing towards us. So it's not the symbol X here, the dot for current up. And then surround it has a circle. And then one. This is what we call concentric circles. The radius is different. The rate becomes larger and larger away from the center. So clockwise, not counterclockwise. If it is current into the paper, then it will rotate clockwise. So we say that if the symbol is not at the reaching towards our eyes, out from the paper towards our eyes, if the symbol is from above towards the paper, from our eye towards the paper. Again, so we move on to the coil. So basically, so over here and over here, concentric circles, and then what we do here is positive down, negative up. That means the current flowing upward. So it is counterclockwise. Counterclockwise. This current flowing from up downwards current clockwise using the right hand grip rule. So we see that at the center, the two arrows go the same direction. Thus, we can draw resultant magnetic center. So basically, what we see here is so we have two wires. Both have this is counterclockwise. This clockwise. Then two outpost circles here shows the same direction and they show above. Then we have our resultant field that also shows the same direction. Okay, so this is the single coil. Okay, how about solenoid? So this is basically a coil that is concentric many times. That means there is many single coil in a single solenoid. So for this way upwards and then downwards and then upwards again, upwards and then basically upwards. So how we're gonna do this type of field that we can do it discretely. We analyze it one chord in each time at one time. So circle everywhere here. You know about that, but you don't need to draw this concentric circle. Yeah, just I want to show you the demo. So this from below to the top. So counterclockwise, and this is clockwise, clockwise, and then the same as the rest. We add these two circles over here shows the direction, and we have a resultant inside this line showing towards the left. Okay, so what happened? We have the surrounding here, so it will continue to connect with the each principle for each layer. So basically, if we use right hand grip rule again for this one, but this time our rest of the fingers, the four fingers, showing the direction of the solenoid, the current flow in the solenoid for above view only, the top view. So if the top view is pointing towards the paper here inside the screen, then our fingers, the four fingers, must also show the same like this. Like if you cannot see it, but my thumb is pointing towards the left. If you do, you can see that my four fingers here basically are in a line in the same direction as the current flow in the solenoid, as seen from the top view. So the thumb pointing towards the left, that means it is north. Okay. So basically from magnetic field that we learned during lower form, that the line that we saw earlier based on the single concentric circle, the concentric circle become, and then we have to towards the left as well. So that means the magnetic field out from the left towards the right and then at the right. So basically it's still the same rule here. We apply the same rule, but it's different. The right-hand grip rules, we have to follow the thumb and then we look at the four fingers. But now we have to follow the four fingers first and then look at the result for the thumb to show the north or south pole. Before this, the thumb shows the current flow up or down, and then the four fingers show the clockwise or counterclockwise for straight wire. But now for solenoid, the four fingers shows the current flow, and then the thumb shows the north and south pole. So this so we have two ways to use the right-hand grid rule. First is the single wire case. Second is the solenoid case. Both cases using the different interpretation of the right-hand grid rule. Thumb for current for single wire, thumb for the north or south pole for the solid. So basically, clearly, make sure each line doesn't touch. Also, more lines here to show our solenoid magnetic field. So I redraw it. More pole magnetic field. And then this is the south pole, the magnetic field into. And then we have to connect the outwards. And we more here to show the magnetic field lines. Okay, so let's move on. Number 6. Compare the magnetic field pattern of a solenoid with a magnetic bar. State the conclusion. So basically, it shows the same. Basically, it shows kind of the same, but we draw it simple here. This is more. So that's the conclusion that we can draw from that reason. So again, but in this case, we don't draw inside the magnet, but actually it exists, do exist. The line inside the magnet do exist, but we don't draw it because the magnet is actually a solid. We don't care much about the line inside the magnet. But in our case of the solid, we need to draw the line because it's not solid, it's a hollow inside this. Solid not here. That means that there is visible lines that we drew up if we put some iron fillings inside it. Okay, number 7. Diagram shows an electromagnet. Current magnet when current flow in a conductor. Is the definition of electromagnet. Because it's not permanent. It's only become magnetic when current flow. If there is no current flow, then it's not a magnet. So that's the term temporary here. So the second condition is must be current flow in the conductor. So again, one question that I would like to address here, if the wire in our house, the electrical wire or the mouse wire or the computer's wire or any types of wire socket, even though there exists current flow, if we switch on the switch, then there exists current flow inside the wire. But why the wire doesn't attract magnetic? So the answer is quite simple. The answer is the magnitude of the current flow inside the wire is smaller. Thus, the strength of the magnetic field smaller. Doesn't have enough strength to pull out the magnetic field around it. But if we increase the current, magnitude of current larger than the normal one, then it probably will attract some of the magnetic object around it. So be careful with wires in your house. You don't need to put it nearer your phone or smartphone because it will interfere with the wave, the electromagnetic wave, such as the radio wave from your phone or the microwave or something like that. So make sure that you put it very far away from other communication device. Okay, B, what is the but if you iron or metal or any type of core inside the solenoid that we run it the core is here the constant the magnetic that is collected magnetic field accumulated concentrated it. So the magnetic field become more stronger. Okay. Give 3 so first thing that I already stated before, in order to make the wire in our house to attract magnetic object, we need to increase magnitude of current. Use thicker wire. This is low, higher current. Again, number 3, of soft. This one is to concentrate the magnetic field. Number increase number of solenoid only. For solenoid. But if it's a coil or a single wire, then number 1 and number 2 is the only factors to increase the strength of electromagnet. Okay, the iron core is replaced by soft iron core. Is the advantage by using soft iron core. So soft iron core can be magnetized and demagnetized. So what it means that if we supply current through the conductor that wind up around the soft iron core, the wire carries magnetic field. Thus, the magnetic field is collected in the soft iron core, concentrated it becomes stronger. Then when we off the switch, there is no current flow, then there is no magnetic field around the wire. Thus, the soft iron core should also doesn't have any magnetic field left. So that's what it means that it can be magnetized when the current flow and demagnetized when the current doesn't flow easily, like in a very smaller time change from on to off for the soft iron core. So as soon as the current flow, it becomes magnetized. As soon as the current doesn't flow, it becomes demagnetized. What happens if we use other materials that is not soft iron core? Basically, when the current flow, current flow in the wire, the conductor, the magnetic field around the conductor will take times to become magnetized for the core. For the core to magnetize, it will take some time. And then when the current off again, there is no current flow in the conductor, there is no magnetic field around the conductor, then still exists some of the residue of the magnetic field in the core. So if we use a different type of soft iron core, this type of problem still exists. So we don't want that. We want if the current flow, then there is a magnet immediately, and then if the current is off, there is no magnetic field immediately as well. So that is the good one for soft iron. Polarity of the solenoid is high because the electrics on the current here from below to upward and then back, front, back, if we use our right hand rule, my thumb is towards the right. Make sure that you know. And the fourth thumb here, showing from my eyes, is towards downwards. Showing towards the downwards, so the thumb should be on your right. Okay, let's see B. Downwards, downwards, downwards. So again, in direction as well, should be off. Positive, negative, upwards, upwards, upwards. So this left. The left. Now the rest four fingers is up. So this is not four. This is a terminal arm and current in sub four. So sub four and not four. The track is sub four again, but it's also so it will read like this is track. Attracted the solenoid made you or have okay, number diagram shows an electromagnetic or relay. So use relay exclusively from electronics. For this, we already learned function to stir on secondary circuit which has higher voltage. Okay. The transistor that we want to use or the logic gate that we want to use only use a very small voltage. If we want to combine it with a motor or a pump which use a larger voltage, it will damage the transistor. Thus, we need some kind of intermediate between the primary circuit and secondary circuit to communicate between these two. So we use the relay switch in order to do that. So why the power of the higher and how the relay function as. So let's do the first question first. Why the relay soft higher or can magnetize and demagnetize easily? So we already know, but doesn't need to explain it more than we should here. So how the relay function as a switch, then this we can treat this question as 4 marks explanation question. So basically, so our start should be current flow when the switch closes. When the switch is closed, current flow solenoid. Next, because the solenoid carries current inside it and then produce magnetic field around it, and then that magnetic field is catched, is collected in the soft iron core. Because the soft iron core become magnetized, it will attract soft iron element towards it. So, amateur over here. So basically it will attract it towards the soft iron, and then this switch over here, as soon as this move, this switch over there is pushing, that's the contact, touch each other. This contact there. Yeah, and result secondary secondary circuit current. So that is the basic things that what we call it working principle for relay as a switch. So if you want to only if switch off or open, there is no current flow. Thus the soft iron core demagnetized. The soft iron armature will move away from the soft iron core due to springy metal over here. Springy metal over here will push the soft iron core downwards, causing the soft iron core to move away from the soft iron armature to move from the soft iron core. Thus, the contact doesn't touch each other. Flow in the circuit, or the secondary circuit is open circuit. Let's move on to the next question. Diagram shows an electric bell. When switch is on, the bell rings continuously. Explain how the bell can ring continuously when switch is on. So again, we can use this question as a 4 marks explanation. When switch is on, current flow into the solenoid. Next, iron core magnet. Concept here will the hammer hit the gong and produce result. Contact the does not touch that not touch each other with the armature, the soft iron armature, causing the circuit to be open and current not flow. So basically, it will causing to be off again, and then there is no current flow inside the solenoid. There, the soft iron core demagnetized, the springy steel strip pull away the soft iron armature from the soft iron core, causing contact to touch again. So when the contact touch again, current will flow and into the solenoid, the soft iron core become magnetized again, and then the hammer or the soft iron armature will be towards the soft iron core. The hammer will hit the gong, produce sound, so it will repeat the and the process will to end up our explanation. Okay. B. Explain how to produce louder sound by following aspects. So basically, this is a modification. Modification different question. Okay. So let's draw our table here. So make sure that you don't repeat answer or the question that is given. Do not call back all the relevant keywords in the question, such as produce out sound. You cannot see that as your reason. So we must make a synonym or other rephrase the terms in other words. So let's number the growth, number turn column. So more reason produce stronger magnetic field. But the reason is you can repeat if you don't have any answers. You can repeat the relevant reason. But it is not encouraged for you to do that. You must find other reason that you can use. Big form. So the should be produce louder sound, but since the word itself are in the question, so we must use other terms. Produce larger amplitude wave. Then it will become thing, but still explain the same thing, which is amplitude represent the loudness. If we want to produce louder sound, that means larger amplitude. Elasticity. Because high spring constant, that means larger force produced, or larger elastic potential energy stored, thus larger kinetic energy as well. So basically, high elasticity means that it's easier for the object or the spring to return to its origin. To return to its original shape, that means it has a larger force, restore force we call it, to make it normal again. Larger force is already enough. Larger force. Okay, shape of the soft iron. It must be shape of a U magnet or radial, like circle, but the circle cannot be used here because we don't anything. Or what I mean is, if the shape is like a donut, then the center of the donut should be something there, but we don't put anything there. We just put the armature beside the donut, so we don't actually need to make it a shape of the donut, but the shape of the U shape. We have hole from the U shape. So if I draw it, look like this. So we have north pole and south pole. So we have two poles to attack the armature instead of just one pole. We round it. If this is the north pole, it only have one pole to attract the armature. If we use the U shape, we have two poles, thus stronger magnetic field. Use larger design, larger range. Think about another reason that is not the same as the first one. So let's think. You can say produce more concentrated magnetic field. So lastly, the thickness of the core. Coil. So again, this is a factor of resistor. So with one smaller resistor, so we say thicker, smaller resistor for more current flow. Current flow. Okay. So in this case, for modification, make sure that you have 5 points for 10 marks. Okay. So I think that's all for today. You remember how to use the right hand grip rule. There are two ways to use. One is for the straight wire or the coil. The second one is for the solenoid. Thumb towards the current and thumb towards the north pole. So it's different ways to use it. So make sure that you realize that both have the same rule. Right hand grip rule. Okay, the field pattern, concentric circles, the resultant field, the solenoid, everything, the direction, everything that we need to know, the factors of the strength of the electromagnet, how to explain relay switch, how to explain bell, emergency bell, as well as speaker as well. So make sure that you know all of the things before we move on to the next concept tomorrow. Okay, that's all from me today. Thank you.